Hey everyone, and welcome to this tea time talk. So off-policy deterministic policy gradient, or off-policy DPG. So first, describe the problem and some basics, and then I'll review the previous work in off-policy DPG and show a few lines of derivation. This previous work is an approximation of the gradient, and I'll show a few lines of the derivation to see what that approximation means and how it comes about. And then I'll show an example to see what can possibly go wrong with that approximation. The problem is off-policy control with continuous actions. So we have a behavior policy mu with a state distribution d mu that we will use. The agent uses this behavior policy to take actions in this beautiful diagram. And then after the interactions with the environment gives the samples of the next state and reward. And with those samples, we want to learn a deterministic policy pi to maximize performance. So our target policy is deterministic here. And now what's a deterministic policy? What's performance? A deterministic policy is a policy that's deterministic. So you give it a state, it gives you an action instead of a probability distribution over actions. And you can parameterize it, for example, with this parameter theta. So you have a parameterized function and you can learn it. One problem with the deterministic policy is that it can't explore well, because for a good exploration, you may need to take a different action once in a while to explore different parts of the environment. So the way people train it in practice is off-policy. So they have a stochastic behavior policy that can explore well, and they use that to train the deterministic policy. And in this paper, this is the famous DPG paper, and they first propose an on-policy method to learn the deterministic policy. And then they say now this on-policy method remains theoretical and pedagogical because you can't explore well with that deterministic policy. And then they go on to propose an off-policy method. So you have a stochastic behavior policy, and you can train your deterministic policy with it. And that off-policy method is gradient ascent on this objective function. So the objective function they define is the state values with your deterministic policy, and the state value is just the sum of discounted rewards after the state, and weighted by the d mu, the behavior policy's state distribution. Now this choice of objective function as to why this objective function is a whole other story, but feel free to ask me at the end why this objective function. But for now, let's just stick with this one and just derive the gradient, because we want to do gradient ascent on it and improve it. The good thing about this weighting here is that it's a behavior policy's state distribution, so it doesn't depend on our parameters. And if we want to take the gradient of this objective function, it just becomes the gradient of state values weighted by that weighting we had, the behavior policy's state distribution. Now let's see what the gradient of a state value is. The gradient of state value is just the gradient of action value with the action that you would take with your deterministic policy. So it's the sum of discounted rewards after you take that action in that state. And this equality here is true because you have a deterministic policy and there is no chance of taking any other action. You only have this one action here. And then instead of this action value here, you can write the next reward plus discounted expected next state value. So you have the gradient of the next reward plus discounted expected next state value. This gamma here is the discounting factor. I'm using a constant discounting factor just to make the derivation short, but it also extends to transition dependent discounting factor. Just the derivation becomes a bit longer, but the idea is the same. And this P here is the transition probability for going to S prime from state S if you take this action here. Now we can just move the gradient in these things. So we have the gradient of the reward plus discounted gradient of the product of transition probability and the next state value. So we have the gradient of the product of these two things here, and we can apply the product rule here. So then we'll have the gradient of reward didn't change, discounted gradient of transition probability times next state value, transition probability times the gradient of the next state value. All Or you can think of it this way. We have the gradient of reward. Gradient of transition probability is weighted by the value of the destination. Gradient of next state values weighted by the probability of transition into them. And what this derivation here means so far is that this gradient of state value wanted to give you a direction so that you can move your parameters in that direction and raise the state value. And if you want to raise the state value, you will raise the reward. You'll raise the probability of going to higher valued states. You'll also raise the value of the states that are likely to follow. So this is what each of these three terms here means. And these two terms are also discounted. Now, in the on-policy case, they continue the derivation and find the gradient. But for the off-policy case, it actually becomes a bit harder to continue the derivation. So they drop this third term and settle for an approximation. So the approximation is just the first two terms. So we have the gradient of reward, gradient of transition probability times the state value, but we don't have the transition probability times gradient of state value. So it means you'll raise the reward, you'll raise the probability of going to higher valued states, but you'll not try to raise the value of the successor states. And then we can now continue the derivation. So we have the gradient of reward with the action, and this action here is a function of our parameters. So we can apply the chain rule here. We will have the gradient of reward with respect to action times gradient of the action that we will take with respect to our parameters. And same here. So we have the gradient of the probability, this transition probability with that action. And we can write it as the gradient of, with respect to our parameters. And we can write it as the gradient of the transition probability with respect to action times the gradient of the action that we will take with respect to our parameters. And here we have this term that appears here, gradient of the action with respect to our parameters. Again, gradient of the action with respect to our parameters. And we can factor it out, put it behind it. So you have the gradient of action with respect to our parameters times gradient of this whole thing here, the reward plus transition probability times the next state value with respect to the action that you will take, only the immediate action here. And we can write this reward plus discounted expected next state value as the action value again. So we'll end up with this. We'll have the gradient of the action value with respect to action times the gradient of the action that you take with respect to our parameters. Now, this thing here and this thing may seem similar, but the difference here is that here, before the approximation, you had the gradient of the action value with respect to our parameters, and you wanted to move the parameters to increase the action value. And it would amount to increasing the reward, increasing the probability of transitioning to higher states values, and increasing the value of the successor states. But here, you have the gradient of the action value with respect to only the immediate action. And it means that now after the approximation, it's like that the agent is assuming other states have a fixed value, and it only controls the immediate action. It only adjusts the immediate action to make the most of this situation, and it will not try to increase the value of the next states. Sure.
Why couldn't you have gone straight from the top to the bottom?
Because I wanted to see what
just
drops you.
Without all those steps, because you just, by the same step, use the chain rule, just go from the top to the bottom.
Yeah, I wanted to point out what happens in between and what drops here. Because I wanted to point out this here.
From the top to the bottom by the chain rule. Now you look at the top. The only way theta influences.
Let me think about it.
I guess it's right. It influences it in two ways. Both through the action.
Yeah, it's not just the function of the action. It's also a function of our parameters, because the other states have a value that depends on our parameters.
Okay.
Yeah. Right. Okay, so this is the approximated gradient of a state value. So it's the gradient of the action value with respect to the immediate action only, times gradient of the action that you take with respect to our parameters. And if you remember, the gradient of the objective function was gradient of state values weighted by d mu. So we can just write this as the approximated gradient of state value. We'll have this as the approximated gradient of the objective function. So the approximated gradient is what we had in the previous slide, weighted by d mu. Now we also derived the actual gradient. I'll just call it the true gradient, the gradient without dropping that term. And it turns out it becomes something similar to this, but keeping that term changes the weighting from d mu to this other weighting ms. And this ms weighting is something that satisfies this equation. It's the solution to this equation here. And now this talk is too short to go over that derivation, but I just put the final form here because I want to compare it in the next slide. So this is the approximated gradient. This is the true gradient, and we've found them. But if you want to use an online algorithm to learn these things, to learn the policy from the samples, we have to estimate some things here. For example, we don't have the gradient of action value with respect to the immediate action readily available, and we don't have this weighting here readily available. For estimating this thing here, the DPG paper proposes a way to use a critic component and use that to estimate this part here. And for these weightings here, well, we don't have an algorithm so far to estimate this. It's a future work to find a solution to this equation so that we can use that as the weighting here to learn with the true gradient. But in the example I'm about to show, I'll just feed the agent with the true values of these things that we wanted to estimate based on my knowledge of the environment, because my goal is to compare these two forms fundamentally, not the algorithms that are based on these two things. And I want to rule out any algorithm-specific estimation errors. So I'll just, I know these things that I wanted to estimate based on my knowledge of the environment, and the environment is small, so I'll just feed that to the agent and train it with the approximated gradient and the true gradient. And yeah.
Is this M thing related to the emphasis?
Yeah, that's right. Yeah, that's right. Actually, for the stochastic, when the policy is not deterministic, the stochastic policy, we actually have an algorithm, and it turns out if we use the online algorithm that was used in that emphatic TD paper, we can turn the weightings to this M. But the problem is that this weighting here, the emphatic weightings need important sampling ratio. And important sampling ratio is so important sampling ratio at time t, can you see that? Important sampling ratio at time t is the probability of taking that action under the target policy over the probability of taking that action under the behavior policy. And we'll use that for a stochastic policy. But if the policy is this pi here is deterministic, it means only one action has probability 1 and all the other actions have probability 0. So only one point in the action space has probability 1, and when we want to use that, all our important sampling ratios become 0, so we can't have that. And this is the problem. This is why we can't estimate this emphatic weighting so far for a deterministic policy. Okay, now just to recap, there were two important things in the approximated gradient. The first thing was that from each state, the agent is assuming the other states have a fixed value, or that the value doesn't depend on our parameters, and it will only control its immediate action. It will only adjust its immediate action to make the most of the situation, and that the states are then in the overall gradient weighted by d mu. So look at this example here. This example has 3 states and this terminal state here, and And this sigma that appears everywhere is the logistic sigmoid function. We have a continuous action. It's a scalar real-valued action. And this logistic sigmoid basically just shrinks the range to 0 and 1. So it means if our action is a negative number, that sigmoid is between 0 and a half. If our action is a positive number, that sigmoid is between a half and 1. And these lines that start with R show the reward for each transition. And these two lines are transition probabilities, because this one is a stochastic transition. So what these things mean is that from a state S0, if you take whatever action you take, you get a reward 0. But if you take a negative action, you're more likely to go to this state. If you take a positive action, you're more likely to go to this state. From a state S1 and S2, all transitions lead to the terminal state here. And for S1, the reward ranges from 2 for negative actions, for large negative actions, to 0 for large positive actions. For S2, the reward ranges from 0 for large negative actions to 1 for large positive actions. So in state S1, negative action is better. It gives you a reward almost to 2. In a state S2, a positive action is better. It gives you a reward of almost 1. And the discounting factor is 1 everywhere except when you go to this terminal state where it's 0. And the behavior policy just everywhere samples actions from this distribution, normal with mean 1 and variance 1. So it means the behavior policy takes most of the time takes positive actions. And from state S0, the behavior policy would go to S2. It means d mu of S0 and S2 are very large, and S1 is rarely visited and has a very tiny d mu. Now, the catch here is that S1 and S2 are alias to the agent, and the agent doesn't know in which one of these two states it is, and it has a single parameter that controls the action in both of them, and it has to take a similar action in both of them. Now, the best the agent can do in this situation is to take negative actions everywhere all the time, large negative actions. Because with a negative action, it'll go from S0 to S1 and get a reward of 2. So the value of S0 will be 2. Value of S1 will also be 2 because it gets a reward of 2 before termination. Value of S2 will be 0. That's unfortunate, but inevitable because it has to take a similar action in these two states. So we initialize the agent close to this optimal policy to take large negative actions everywhere and train it with this behavior policy once with the approximated gradient, once with the true gradient. And this is the result. So this is what you observe. And this x-axis is just time episodes, and this y-axis is the objective function that we wanted to maximize. When you train it with the this DPG here is the approximated gradient. The true DPG is the true gradient. And when you train it with the approximated gradient, it actually reduces the objective function until it settles on a suboptimal policy.
Can you say what that y-axis is again?
It's that objective function we had that we wanted to maximize. State values weighted by d mu. Sum of state values weighted by d mu. Okay. So when you train it with the DPG, it reduces that objective function until it stops here.
The expected return?
The expected return. The weighting here is the behavior policies, state distribution. If you plot episode returns, you'll also see something like this. So it's the same drop here and it's the rise here, because the episode returns is just the value of S0. And so now why this happens? Why does DPG reduce the objective function that it wanted to do gradient ascent on? The thing is, so if you remember those 2 points about the approximated gradient, at each state the agent wants to adjust the immediate action to raise its value, and the states are weighted by d mu. Now, in state S1, negative actions are better. In a state S2, positive actions are better, right? But we have the same parameter that controls the actions in these two states. So S1 wants to make that action more and more negative. S2 wants to make that action more and more positive. So there is this kind of tug of war between these two states. And which one is the winner? The second point about the approximated gradient was that the states are weighted by d mu. And with that behavior policy, d mu of S0 and S2 was large, and d mu of S1 was tiny. So S1 here is insignificant, and S2 is the winner, and S2 makes that action more and more positive. And you can see that in this plot here. So we started with a negative action because we wanted to be close to that optimal policy. And this y-axis here is the action the agent would take in the earliest states. And this x-axis here is, again, episodes. And when you train it with DPG, S2 is the winner and makes that action more and more positive, although it was negative in the beginning. So these actions here become more and more positive. And when that action becomes positive, S2 has a good situation. So S2 has a value of 1, and S0 has a value of 0. Because S2 has a value of 1, S1 has a value of 0, because S1 wanted negative actions. And what happens with S0? S0 can only control its immediate action to make the most of this situation. So S0, from a state S0, the agencies, it has this state S2 that has value of 1. It has a state S1 that has value 0. So it's better to go to this state. And from state S0, the agent also will make that immediate action more and more positive. So that final policy that DPG stops on is to take large positive actions everywhere. So it'll take a positive action from S0 to go to this state and get a positive action again to get a reward of 1 before termination. But we started with negative actions, which was actually a better situation. So that's why the DPG here actually reduced the object function. That's why DPG found a solution that was actually worse than our initial point. Now, why does the true gradient solve this? So when you train with the true gradient, there's still that conflict between these two states, but it actually turns out when you train with true gradient, the situation for S0 is now different. Why? Because if you remember, before the approximation, the agent wanted to increase the action value by controlling the immediate action and also increasing the value of states that are likely to follow. When you initialize it with negative actions, S0 is most likely to go to S1. So if the agent wants to increase the value of S0, it will not only improve the immediate action, but also try to increase the value of S1. And for increasing this value of S1, it has to take this shared action more and more negative. So now it's not only S1 that wants to make this action negative, also S0 is helping it. So in this rope pulling game or parameter pulling game, we have S0 and S1 on one side trying to make this action more and more negative, and S2 on the other side. And now this side is the winner because it has also S0 on it, because S0 wants to increase the value of its successor state. And that requires making that action more and more negative. So it means when you train it with the true gradient without dropping the term, you make that shared action more and more negative, and it shows in this plot here. So this was the action. With the true gradient, it becomes more and more negative, but with the approximated gradient, it became positive. And then you get closer and closer to the optimal policy, which was to take large negative actions everywhere. And you can see that with the true gradient, it actually increases the objective function until it gets close to the highest attainable object function. That's one with a policy that takes large negative actions everywhere. So this is how the true gradient with that extra term solved this situation and this problem here. And now, just to sum up, so we went over the derivation of the off-policy policy gradient in previous work and showed how it approximates the gradient and what's missing in that approximation. And then showed an example to see how these two compare and why keeping that term might be important in some situations. Yeah, that's it. Thank you. Any questions? Okay, sure.
In the previous graph,
Okay.
did you do something to prevent the actions from like going to positive and negative infinity?
No, the actions are no, but because they saturate here. I think it's because this logistic sigmoid function, like that, is the gradient of that logistic sigmoid function that appears in our policy gradient that saturates. I think it's because of that. Okay, sure.
When you have the emphatic weighting,
Okay.
can you go back to the slide for that?
The gradient itself. Okay.
Yeah, so it looks kind of familiar, except for that the probability looks like instead of the next stage, it's predecessor states.
Oh, yeah, right.
Do you have some intuition?
Yeah, sure. So if you remember that example, so in the approximated gradient, the weighting was d mu, and here the weighting is ms. This weighting here is d mu of that state plus the weighting of its predecessors, because in that rope pulling game, its predecessors came to help that state. It's because in the true gradient, not only that state wants to increase the state value, but also its predecessor states want to help this state and increase its value, because it's a successor state to them, and its value matters to them. If they want to raise their own value, they have to raise this value as well. And here is here this S primes here are the predecessors, the previous states. So yeah, this is the idea. Oh, okay, sure.
I have a question about the experiment. So if I understand correctly, if the behavior policy was biased towards the negative actions, then the approximate gradient would also work, because you'd have higher mu on the...
Yeah, I think so. Yeah, yeah. So if the behavior policy was close to the, for example, the target policy where we had initialized and where our final policy was, then yeah, it was almost an on-policy case. Yeah.
Well, looks like we're actually right on time. I think today's a good time to thank Ehsan.
Thank you.